Hello. We're going to talk about section 3 of chapter 10, which is a new kind of problem for us. It's the two population proportion problem. And the main thing to remember about this kind of problem is the type of data that we have is nominal. It's not interval or ratio like we've been working with. And so we're going to be talking about percentages or proportions of the population that have some characteristic. And there won't be any means and there won't be any standard deviation. So like the z proportion problem we worked with before, when you first look at the problem you may think, boy, there's not a lot of information here. But there's enough information to do a proportion problem, which is what we need to do. Okay, so we're going to be examining population proportions, proportion 1 and proportion 2. The assumption we're going to make is that there is no difference between those population proportions. In order to do this test, we do have some necessary assumptions. So let me tell you what they are. Nominal data, as I mentioned, which means we're talking about percentages, and we have to assume a normal distribution. The way to determine whether that's a reasonable assumption is to use this test for normality, which is found on the PowerPoint slide. N1 times pi 1, N1 times 1 minus pi 1, N2 times pi 2, N2 times 1 minus pi 2. All of those products individually have to be at least 5. If they're less than 5, then we can't assume a normal distribution. The main time we're going to have a problem with that is if the sample size is small or the proportion is real large or real small, close to 1 or close to 0. Okay, but as long as we pass that assumption, we have normal distribution, nominal data, independent random samples. Those are our basic assumptions for this kind of test. Okay, we're going to use a sample difference to estimate the population difference. So we use the symbols P1 and P2 to correspond to the sample proportions and pi 1, pi 2 to correspond to the population proportions. Okay, we're going to also use a calculation of something we call P bar, which is the average proportion. To find that, we just take the first sample, we take the number with the characteristic, which we call x1, plus the number with the characteristic in sample 2, x2, sum those values and divide by the sum of the sample sizes. That gives me the average proportion with the characteristic I'm interested in. Here's my formula for calculating z in step 5. It says sample proportion difference minus population proportion difference, which I believe to be 0, divided by the square root of p bar times 1 minus p bar times, in parentheses, 1 over n1 plus 1 over n2. So remember, we've got to find p bar first and then plug it into the formula. That is, sum the x's, sum the y's, and come up with the average proportion. Okay, so there's what our formulas look like. That'll be on the formula sheet. It's not really as bad as it seems. N is just the sample size. P is the sample proportion, which probably will not be given, but we'll tell you how to do that. And then P bar. Okay, for this hypothesis test, again, we can have a one-tailed or a two-tailed test. The answer is going to depend on what is the problem asked for. Does it say, is there enough evidence to say proportion 1 is less than 2 or 1 is greater than 2? Or does it simply say, is there a difference in the proportions? If it says, is there a difference, the two-tail test. If it says 1 is greater than the other, it's going to be a one-tail test. And that's going to determine what our critical values look like. If it's lower-tailed, all of the rejection region is on the lower end. Upper-tailed, it'll all be on the upper end. If it's two-tailed, you're going to have half of the type 1 error probability on each tail. Here's an example. Is there a significant difference between the proportion of men and the proportion of women who will vote yes on proposition A? We took a random sample of 72 men and 50 women. 36 of the men said they would vote yes. 31 of the women indicated they would vote yes. Test at the 0.05 level. Okay, so we have some information here, and we can go to our whiteboard to show you how to use that information to solve our problem. Notice also the sample proportions are not given. We're going to have to calculate them based on the information that we are given. Okay, 31 of 50 was the proportion for the females, and the males, we took 72 of them. 36 of them agreed to vote for Proposition A. So this is for males. All right, I'm going to make a sample proportion out of these by simply turning those into percentages. This one is 0.62, which is 31 divided by 50. 36 divided by 72 is 0.50. So this would be proportion for males, and this would be proportion for females. So those are the sample proportion values that I'm going to need to use in this problem. All right, now I'm going to set up my null and alternative. It asked me whether there was a difference in the two groups, so that's going to be a two-tailed test. So step 1 says proportion 1 equals proportion 2. Notice these are population values, of course, because I want to know about the population, not the sample. HA equals proportion 1 is not equal to proportion 2. Step 2, sample sizes, N1 equals 50, N2 equals 72, and alpha equals 0.05. Remember, as usual, if it doesn't tell me anything, I assume 0.05. Okay, I've got interval or ratio data. It's not talking about means, there's no standard deviations here. So it must be a Z proportion problem. Now I've got to check, I've got two populations. I've got to check to make sure that I can use this approach. So remember, I've got to do the test for normality. N1 times the proportion, and I think the proportion is, if I don't have the population values here, which I don't exactly, I could use P1 and P2, or the proportion for females and males. So I'd have P1, and then it's N1 times 1 minus P1. Remember, these are the four combinations I need to test. N2 times P2 and N2 times 1 minus P2. All of those products have to be at least 5. Okay, so my sample sizes are 50 and 72, and my proportions are 0.62 and 0.5. So let's take the smallest one, that'd be 0.5 times 72. So my sample size would be 72 times 0.5, that's going to equal 36. So that's well above 5. If I did it for, let's say, one of the other ones, 0.62 times 0.5, I'm going to have 31. So I'm still way above 0.5. Remember, it has to be greater than or equal to 5. And it is. So that means it looks to be normally distributed. So I'm ready to do Z proportion. Okay, step 4. I need my critical value. This is going to be a critical value of Z. It is alpha level 0.05. It is two-tailed. So therefore, critical value of Z is going to equal plus or minus 1.96. I can look in my table to find that. Remember, the area would be 0.025 in each tail. Okay, 1.96 and minus 1.96. There's my rejection region. Here's my other rejection region. Okay, now I'm ready for step 5. Step 5 says plug into the formula. Okay, the formula we're going to use is found on page 332, in the middle of the page. I've got to find P bar first, so let me do that first, and then we'll be ready to plug into that formula. P bar equals X1. Okay, let's go up a minute so we can see our numbers again. Okay, one of them was 31 plus 36 divided by the sum of these, which is 50 plus 72. So we have 31 plus 36, 67, divided by 122. So that's going to be the value for my P bar when I work that out. It's going to be a little bit more than 0.5. Let's see, we can look here in our chapter and see exactly what it is. It is 0.609. I'm sorry, that's not the right page. Let's see. Okay, P1 is damn you stupid thing. Where's the the value that I'm doing? Okay, well, it's about 0.5, somewhere in that area. So we can say approximately equal to that. All right, so now we're ready to go to our problem and see what we get. Let's go back to the PowerPoint and we can find out what they came up with for an answer. Okay, so our p-bar value is 0.549. That is, summing the x's and dividing by the n's. Notice it should be somewhere between 0.5 and 0.62. That way we know that we've got the right value because it does seem to be an average of those two. Okay, the calculated value now in step 5 is found by plugging that number into the formula and solving, and we end up with minus 1.31. That value is in the fail to reject region, so I'm going to fail to reject the null in step 6, and I'm going to have 0% confidence because I'm failing to reject, but what I think is the population proportions, pi 1 and pi 2, may in fact be exactly the same. There's not a significant difference in the proportion who will vote yes and no between men and women. I have 0% confidence because I failed to reject. I'm not willing to change policy based on what I figured out. Okay, so that's a sample problem of that, and let's try one more in the textbook here, and then we'll be finished with this section of the chapter. Page 338, problem 1036. Let me go through the 6 steps carefully with you so that you can do that yourself. Okay, 1036. Okay, the problem says the percentage of online adults in the United States increased from 63% in 2000 to 69% in December 2003. In 2003, 25% of online adults used the internet to gather data about products and services. This result was based on a sample of 500 adults. 2003, 299 of 729 online adults who were sampled used the internet to gather data about products and services. So let me begin to write down some of the information they're giving me. In the year 2000, 25% of 500, that was N, 2000 we had a sample of N1 equals 500. Okay, then we had the year 2003, and that percentage could be calculated based on 299 out of 729. Okay? So we sampled 729, 299 of them used the internet to gather data. 0.05 level, that's what it tells me. As usual, I would have done that anyway, 0.05. Is there evidence the proportion of online adults who use the internet to gather data about products and services is higher in December 03 than in 2000? Okay, so because of that keyword higher, my first step is going to say proportion in 2000, proportion in 2003, and again, let me read the question so I know what it is I'm trying to find out. Null hypothesis is proportion in 2000 is, what I'm trying to prove is there evidence that it's higher in 2003 than 2000? So this is my alternative hypothesis. Proportion 2003 is greater than the proportion in 2000. Or you could say proportion in 2000 is less than the proportion in 2003. So this would be greater than or equal. That's step 1. Okay, now again, I could have put 2003 over here on the left and 2000 over here and reversed my sign, but whichever way I decide to do it, I have to be consistent from then on. I've got to keep the columns lined up. Step 2, I need my sample sizes. N1 equals 500. N2 equals 729. Alpha equals 0.05. Step 3. This is a Z proportion problem. 2 populations. Okay, now, assumptions, remember, normal distribution. Interval or ratio data? No, this is nominal data, which means we're talking about percentages here. Nominal data, normal distribution, 2 populations, and I'm interested in proportions. Okay, with this kind of test, however, I could have a 1 or a 2-tailed test. Right here, I have a one-tailed test because the sign is less than. Step 4, I need a critical value. It's going to be a critical value of z because it's a z problem. And it's a lower tail test, so that means it has to be negative. It's going to be 0.05, but it's only going to be one-tailed, so it's going to be 1.645 negative. You can look that up in your table if you want to. You're looking up the area 0.05, and that's what you're going to get, minus 1.645. Okay, if I get something down here, I'm going to reject. Otherwise, I'm going to fail to reject. So I'm ready for step 5. Before I go into step 5, however, remember I need to find a p-bar value. Okay, notice in my formula I need p-bar, so I'm going to have to calculate that first. I'm also going to have values for p1 and p2. So let's go back over here. Come on. Okay, so to find my proportions, I would take 25% of 500. So P1 equals 125 out of 500. That's 25%, which is what they told me. Okay? And P2 equals 299 over 729. So that's how we'd find the other proportion. So one of them is going to be 0.25. The other one is going to be 299 divided by 729. Okay, that is, this is not the problem that I want. Okay, that's not going to help me. Let me look it up. Okay, so I'm going to have to find each of those separate proportion values, and then I'm going to have to find the combined proportion value. All right, this is problem 1036. So let's look up our answer here. And we have 0.4102 is the other proportion. Okay, so this is 0.4102. 4102. So it's 41.02%. This one is 25%. So now I can find my combined by proportion, P bar, by adding up the x's, 125 plus 299 over 500 plus 729. 729 plus 500 is 1229. And the numerator would be 125 plus 299. And that would give me then my P bar value, which is 0.345. Okay, that's the value I get for P bar, is 0.345, which is in the middle of 0.25, 0.4102. So it looks like it's probably pretty reasonable. So now I'm ready to plug into my formula to see what I come up with. So I take the sample proportions, 0.25 minus 0.4102 divided by square root of P bar, which we just found, 0.345 minus 1 minus P bar. I'm sorry, this is multiplied by that. That is 0.655. Okay, and then I've got to have 1 over N1, which is 500, plus 1 over N2, 729. These are in parentheses, so you've got to do the part in parentheses first. Multiply by 0.345 times 0.655, and multiply that then by what I got in parentheses. Then take the square root and divide it into the difference up here on top. So my answer there should be minus 5.80. Okay, that's my calculated value for step 5. Now I'm ready to plug into step 6 and summarize my answer. Step 6, this value is way down here, minus 5.8. Reject the null. Rejecting the null. High level of confidence. Notice how far this value, 5.8, is below the 1.645. So I'm going to have certainly at least 95% confidence. Really going to have a lot more than that. And what I think is proportion 1 is not equal to proportion 2. Okay, so I'm going to change policy, and just looking at the numbers, it looks to me like my answer is probably going to be sensitive to alpha because the numbers are so different. Minus 5.8 minus 1.645. So I'm going to calculate a p-value, and then I'm done with this problem. To find my p-value, I go to step 5, 5.8 negative. I'm going to look in the table, which corresponds to z. I'm going to look up 5.8. This is a z value, remember, so I've got to go down the left column to find that value. And I want to get as close to that value as I can get, which is going to be 5.5. Okay? And 5.5 is 0.00000019. So in this case, I've got 1, 2, 3, 4, 5, 6, 7 zeros, and then 19. And notice that's 5.5, and I've got 5.8. So I've got 7 zeros and then a 19. So I'll write it down. P point 1, 2, 3, 4, 5, 6, 7, 19. And it's actually going to be less than that value because remember that only corresponded to 5.8. So my confidence level is 1 minus that, 99.99999% confident, approximately. Okay? Very high level of confidence, not sensitive to alpha because this confidence level is so high and p is so small. It's almost 0, which means I've got almost 100% confidence in my decision to reject. Okay, so that takes us through to our second exam. And now what we want to do is just review a little bit for that exam, and then we will pick up with analysis of variance after this test. Okay, let's see what material we've covered on this last exam and make sure that you're pretty familiar with it before we turn you loose for today. Okay, we talked about control charts. We'll give you a formula sheet as well so you can kind of be looking over this at the same time. Control charts, we have 2 types. Our basic purpose in doing control charts is to make sure whether the process is operating normally or not. We're really testing a hypothesis that the process is normal. That's the null. And the alternative is that it's not normal. So we've got P charts and we've got X bar and R charts. Those are the types of charts that we've looked at. The difference is the type of data. P charts are used with nominal data. All we know is out of a certain number, how many of them had a particular characteristic we were interested in. So we're talking about percentages. We're going to have large samples over here. Remember, the samples can be as large as 100 or even 1,000 in each sample. The tricky part in doing these problems, remember, is knowing what n means and what k means in the formula. So make sure you know which is which. N is the number of observations that you take in each period. K is the number of periods on which you took observations. So make sure you don't turn those around and end up with incorrect control limits. Remember, we take 3 standard deviations in either direction then. We've got to find P bar, and then we take our 3 sigma limits. Remember, proportion problems. Proportions will never be negative. They've got to be between 0 and 1. When we talk about the range and the mean over here, X bar and R, remember we have to do the range first. Now we have not nominal data anymore, but interval or ratio. With this kind of data, we're going to have small samples. We're only going to have 3 or 4 or 5 maybe in each sample, maybe 8. That's as big as it gets. Small sample size. Okay? And you've got to do the R chart first. The range is just an estimate of the standard deviation. It's simpler to calculate. That's why we use the range. And the range, because it is the smallest minus largest value, or largest minus smallest, I'm sorry, it has to be 0 or positive. Cannot be negative. Neither P or R can be negative. Only X bar can be negative. A mean can be negative because we could have negative values for the mean. Okay, we've got to find the range first. Some of the values that we need for this, remember, are going to come from the control chart factor in the back of the book. To look those up, what you need to know is how many did I have in each sample? That's N again, remember? And that's going to be a small number, somewhere from 3 to 6 or 8 or 10. That's what you need to look up, not the number of periods on which you took observations, which is K, but the number in each sample. That's what we want to know. Okay, so that was control charting. The purpose is to find out, is the process in control? Is there any trend? If we have even one data point out of control, it's out of control. We want to fix it and go on from there. If we find a trend, which means values above or below the average, or going up or going down, 8 of them in a row, that's called a trend. We want to identify that before it becomes a problem. Control charting is simply an application of hypothesis testing. That's all it is. Okay, that was chapter 14. We covered sections 3, 4, and 6 in that chapter. Then we went on to chapter 10. In chapter 10, we talked about two population problems, but now we have interval or ratio data again. Just kind of like we had over here, but we're interested in the mean, or we're interested in the proportion, or we're interested in the variance. Those are the three types that we looked at in this chapter. If it's a mean problem, it could be Z, could be T for equal variances, or it could be T for unequal variances. If it's a proportion problem, it's got to be a Z proportion, which means it has to be normally distributed. And if we do the variance, it's going to be an F-test. The F-test, remember, we always treat as two-tailed. We're going to have an upper and lower rejection region for the F-test. Okay? All of these assume a normal distribution. Z-test, T-test, Z-proportion test, F-test. All of these are normally distributed. Okay, how do we distinguish between them? Remember, the Z-test has known standard deviations. T-test does not. It only has sample standard deviations, not population values. And the unequal variances, T-test, we do if we don't have equal variances, if we fail the F-test. Okay? The Z-proportion test we use with nominal data. That's the only one of those, except for the P-chart, that we'd be using nominal data. Okay, that's a pretty good review, hopefully, and if you have questions, let me know.